Today we are going to talk about exponential growth and decay. So we have exponential growth, and for the growth we're going to see that this graph is going to increase from left to right. Okay, and in this equation we have a b to the x. Now a is going to be our starting value. In this case we're going to use the starting value of 1. And as long as b is greater than 1, this is an exponential growth. So let's look at this graph, okay? Our a is equal to 1, and that's our starting value. Our starting point is also our y-intercept. And our b is our growth or decay factor. Now, if a is equal to 1, okay, again, if a is equal to 1, then you can find your b value by looking at the point 1, comma b. In this case, my b value is going to be 2. So if I had to write this equation, my equation would be y equals 1 times 2 raised to the x power. Now, you don't have to put the 1 there since it's not going to do anything, but just so you remember that the 1 is the starting point. Something else about an exponential graph is it's actually, even though it looks like it's touching the x-axis is actually an asymptote. And even though this line is going to get really, really close to the x-axis, it's never actually going to cross it or touch it, okay? So let's look at a decay. A decay is flipped from what we see, okay? In this case, when we did a is equal to 1, notice that this graph is decreasing from left to right. The y value is going down. Again, that x-axis is an asymptote. It's not going to cross. Now, this one's a little bit harder to find the b value, but if you have an exponential decay, one thing you have to remember is that your b value is going to be a fraction or a decimal between 0 and 1. Now, if it's exponential, you can never have a 1 value, so notice that neither one of these can be equal to 1. So you're either going to be greater than 1 or you're going to be less than 1. If it's between 0 and 1, it's a decay, and you're going to expect your graph to go down. In this case, our b value right here, and it appears that our b value is equal to 1/2. So if I had to write this equation, y is equal to my a value times my b value, and the x is my exponent. So again, you have an exponential growth when b is greater than 1, and exponential decay when b is between 0 and 1. So now let's look at these two graphs and determine what they are. So this graph is decreasing from left to right, and if the graph decreases from left to right, it's a decay. Our a value is our y-intercept. In this case, our y-intercept is going to be 1. And if the a value is 1, then this number right here tells me what it's going to be. And we can approximate in this case. It looks about 1/4. So we can say that this b value is 1/4. So just like before, we're going to have an equation that's going to be a b raised to the x power. The x is our exponent. So now let's look at the second graph. We see that this graph is increasing from left to right. So this is an example of a decay. The a value is 1 because that is my y-intercept. Now my b value in this case, because a is 1, I can find my b by going to the point x equals 1 and y is equal to 3. So my equation in this case would be y equals 1 times 3 to the x. Again, if you have a growth, your b value is greater than 1, and if you have a decay, the b is between 0 and 1. So now let's go ahead and just take a growth and take a decay, and let's go ahead and evaluate it for certain numbers, okay? I'm going to do the function at -4 for both of them. So these are going to be calculator questions. My function at -4 is going to be equal to 0.5 raised to the -4 power. And so now to solve this, you would most likely just use a calculator. When I plug this in, I get my function of -4 is equal to 16. So then my second one, if I'm plugging in a -4 there, I have this function at -4 is equal to. So wherever you have an x, you're going to put the -4 and put +4. So again, using a calculator, you get the function of -4 is equal to, it's a crazy fraction, we're going to get 325 over 81. And right here, it's best to just leave your answer in fraction form. Okay, now go ahead and pause this video, and I actually want you to try the next two on your own. Go ahead and plug in a 5 into the equations. Pause right here. Hopefully you got these answers correct. So we had 0.5, and I raised 0.5 to the 5th power, and I got 1 over 32. On the second equation, when I plugged in a 5 into the equation, I got 247. Okay, so now we're going to get into exponential models. These are super important. You're really going to want to write these down. We have an exponential growth model, and we have the exponential decay model. Notice that these equations look very, very similar. So sometimes real life quantities increase or decrease by a fixed % each year or some other time period. Okay, the amount y of such a quantity after t years can be modeled by one of these equations. Now, t can stand for years, t can stand for any interval. If we said that something grows per minute, then t would stand for each minute. So y is going to be the total amount. A is your starting amount. If it's a growth, it'll be 1 plus. If it's a decay, you're going to see 1 minus. R is the rate that it's changing. Super important that R is the % increase or decrease written as a decimal. So if we say a 10% increase, a 10% increase or decrease would be written as a 0.10. So a 10%, you would convert % to decimal by moving the decimal place 2 back. It would be 1 plus 10, or decay would be 1 minus 10. So let's get into using those models for this problem. So this says that a value of a car can be approximated by the model, y equals 17 times 0.9 raised to the t, where t is the number of cars since the car was new. So y is the value of the car in thousand. So this car, is it increasing or decreasing? Well, let's look at the number that's in the parentheses. We have a 0.9. A 0.9 is going to be a decay, okay? Again, it is less than 1. It is a decay. So how much is it decaying by? Well, it is 1 minus my rate. So if 1 minus my rate is equal to 0.9, how can I get the R by itself? Well, this is going to be the same thing as doing 1 minus 0.9. So we're basically, you can solve this by subtracting 1 and then dividing by -1, or just 1 minus this number or 1 plus this number will tell you what it's decreasing by or increasing by. So this is going to give me a 10% decrease per year. So to know the value after 5 years, you're going to take this equation that they already gave you, and T stands for years, so we're going to plug in a 5, and we're going to use our calculator to approximate that in 5 years, this car will be worth only about, because it came out to 10.04, and this is in thousands, so we can say 10.04 thousands, or you can move the number over. We would move it over. So that's the correct answer, since they started us with 17. But if they're looking at money, okay, so here's the correct, this is the answer. And if you want to convert to money, you move the decimal point back 3 times. 1, 2, 3. This car is worth $10,040. Okay. So that was an exponential decay. The value of the car went down from 17,000 to 10,000 in 5 years. So let's try this again. So this car, this one's written differently. So you have the value of a car again, and when you bought it, it was 15,000. Now, because we're talking about thousands of dollars, our initial amount's only going to be 15, okay? Because we know that it means 1,000. Now this car is depreciating at a rate of 18%. So key word, it says depreciates. You need to know that this is going to be an exponential decay. Write an equation to model this data. Y equals, my starting amount is 15,000. Now it's just 1,000, so 15. Now it depreciates at 18%. Please don't put 18% there because it's not, it's decreasing each year by 18. So how much are we multiplying it by? 1 minus 0.18. And we're going to raise it to the number of years. So we can take this one further, and 1 minus 18 is 0.82. So every year it retains 82% of the value. So this, either one equation, either the 1 minus 18 will work, or you can simplify that to 0.82. So is this a growth or decay? Well, this value of the car is going down. Now, what would you expect the car value to be in 3 years? Go ahead and try this. See if you got the answer right. So it's 8.27 thousand. Remember, when we find our answers, we're talking about the value in thousands. And so this right here, it's 8.27 thousand. If you want to convert to the actual dollar value, you just move the decimal place back 3 times and you get $8,270. Okay, we just have a couple more questions. Okay, let's go ahead and try number 3. So in 1902, the number of bison was recorded to be 102. Due to rehabilitation efforts, the number of bisons had increased exponentially at a rate of 18% until 1915. Okay, write an equation that's going to model this data. Well, so far we know that at the beginning they started with 102. So my A value is 102. It is increasing, so it's a growth at a rate of 18%. So my B is 0.18, okay? Now, because I am actually adding it, it's going to be 1 plus 0.18, okay? So my rate of increase was 18. So when I write it, it's going to be 102 times 1 plus 0.18 raised to the x value. You can use t, you can use x, okay? X can stand for the number of years. Now you can actually combine, you can take it one step further. 1 plus 0.18 is 1.18x. Remember, if it's a growth, you're going to expect to see a number that's greater than 1 here. Now, what would be the expected number of bison in 1915? Well, how many years had passed? Between 1902 and 1915, 13 years had passed. So when you plug in this into your calculator, you get that the bison had increased from 102 to about 877. Now, because we're dealing with an animal here, we cannot have a fraction of an animal. We cannot have a decimal of an animal. We're just going to say that there is about 877 bison. So hopefully this video helped you practice some exponential growth and some exponential decay. Have a great day.